All right, we are on page number 6 of the Unit 2 packet. We've been talking about electrons. So we left off with Niels Bohr, and we talked about the ring, the energy level model of the atom, the planetary model that Bohr came up with. And so from there, that was related to light. So today we're going to talk about Schrödinger, the next scientist who changed the model of the atom. So in 1926, Erwin Schrödinger developed the modern quantum theory. Schrödinger changed Bohr's theory of energy rings to the modern quantum theory that electrons exist in three-dimensional orbitals. So Bohr's model is sometimes called the planetary model because it appears on paper to look like there's the nucleus and then electrons just circling the nucleus, the way that planets orbit the sun. Schrödinger said that there are three-dimensional orbitals, meaning that electrons aren't just traveling in circles. There's actually some kind of three-dimensional space that they're occupying. What he ended up coming up with mathematically, with really complicated equations, is he calculated that different electrons are going to travel in different shapes for these orbitals. Sometimes they travel in this kind of spherical region, but sometimes they travel in other types of shapes. And so he called these sublevels. The first sublevel is given the abbreviation of S, and there's only one S orbital. It's just a sphere. There's only one way to draw a sphere. He said that sometimes electrons are going to travel not in just spherical shapes, but they're going to travel in figure eights, essentially. So this is a figure eight that's kind of flat in the page, then we have a figure eight that's sideways in the page, and then we have a figure eight that's up and down. And so we see those three different shapes, right? One coming in and out of the page, left and right, and up and down. These are called p orbitals. They look like dumbbells or figure eights. He said that sometimes electrons travel in these types of shapes. The first four look like four-leaf clovers. The last one, to me, looks like a p orbital that fell inside of a donut or a pool inner tube or something. These are called d orbitals. So they have those funky shapes. There's 5 of them. And then our last ones, these get really crazy. The last couple of them, kind of look like d orbitals and that there's lots of lobes. And these first couple kind of look like this d orbital that got sliced and pulled apart. So these aren't something you're going to need to know how to draw, but just kind of wanted you to see the different shapes. When you're looking at this, the total number of s orbitals possible, as seen in this picture, there's only one s orbital. If you look at the number of p orbitals, there are 3 different ways that electrons can travel in that p orbital shape. For d, 1, 2, 3, 4, 5. And if you're noticing a pattern, it's really just the odd numbers, 1, 3, 5. And when we get over to f, we're going to get to 7. Within each of these orbitals that we see drawn on here, it is possible for 2 electrons to live in that same orbital. So kind of picture this as being like a bedroom, and maybe 2 people can live in one bedroom in your house. So that's kind of the maximum that one orbital will allow. So each orbital can have up to 2 electrons in it. Okay. So what that means is if there's only one s orbital, then the number of electrons here that's possible would be 2 electrons for the maximum number of s electrons in that orbital. For the p orbitals, there's 3 of them. Each one can hold 2 electrons, so 2, 4, 6 electrons would be our maximum. If there are 5 orbitals and each orbital can hold 2 electrons, there can be a maximum of 10 electrons in this group of d orbitals. And then 17, 2 each, would get us 14 electrons. And we'll come back to those numbers a little bit later on, and we'll see that those are pretty significant with the periodic table. All right, so 2 questions on here. We learned about the quantum number n back when we talked about Bohr. So this was in our Bohr section of the notes. The quantum number n tells us which energy level the electrons are located in, which is really just which row of the periodic table we're in. For sodium, sodium is in energy level 3, N equals 3 for sodium, and so it would have 3 energy levels around the nucleus. So N tells us the number of energy levels, which is the row number of that element on the periodic table. And the example that I just did was sodium, N equals 3. It's in the 3rd energy level, and so if we were going to draw the Bohr model, we'd have 1, 2, 3 energy levels. And then in a little bit, we'll talk about how these different, S, P, D, and F correspond to those different energy levels. The second short answer question on here is to draw the shapes of just the 2 simpler types of orbitals, the s orbital and the p orbital. So the s orbital is our spherical shaped, it just looks like a circle. And then our p orbitals are the ones that look like figure 8s or dumbbells. So there are 3 different ones, one that's just going up and down, one that's going left and right, and then the 3rd one would be coming out of the page. So one was left and right, one was up and down. The 3rd one should be coming in and out of the page, which is really hard to draw. So I'm going to draw like a little dashed to mean behind the paper. All right, that's going into the paper. And then here's my one that's really bold that's coming out of the paper. I don't know, I can't draw in 3D, but that's coming in and out of the paper. All right, this bottom section, I'm going to fill in some of the quantum numbers, and I just want you to look for patterns. So it's not so important that you fill in all the boxes, or even write the ones that I write. It's just important that you're looking at this and you're looking for any patterns that you are noticing as I'm writing these in. So when we talk about quantum numbers, this is identifying where these different electrons live in the atom. So we already talked a little bit about some of that. How do we know how many rings of electrons we have? How do we know which ring the electrons go in from the periodic table? But now we're going to give them addresses. So if I was going to give an address to the one electron that makes up hydrogen, I would call it 1s1. If I was going to identify the second electron, which would be in the element helium, I would call this 1s2. And then if we were going to continue on over here, I would have 2s1 and then 2s2. Okay, so I want you to look at what we filled in so far, kind of think about any patterns that you're seeing so far. I'm going to continue on. My next section over here would be 2p1 and then 2p2, 2p3. Okay, so based on that so far, I want you to think about a pattern, and I want you to think about what you would predict for this next box. What would be your best guess based on the patterns that you're seeing right now for what I would write there? My next box would be 2p4, so if that was your guess, good job. And then 2p5, and then 2p6. Continuing on down to our next row, we have 3s1 and 3s2. And then continuing on over here, 3p1, 3p2, 3p3, 3p4, 3p5, and 3p6. So hopefully you're starting to notice some patterns as we're going through and looking at this. So some of the patterns that you might notice is that all the electrons in the first row, we've written a 1 in front of, right? That's our row number. Everything in row 2, we wrote a 2 in front of. Everything in row 3, we wrote a 3 in front of. So that's one pattern that you might have noticed. Another pattern that you might have noticed is that the ones that I wrote over here all have the letter S. Another pattern, The ones that I wrote over here, with this one exception, all have the letter P. Okay. So if I asked you to guess what this box would be based on our patterns, you might see 1, 2, 3 and guess that the next one would be a 4. That's correct. And then you might notice that all of these are S's and guess that this is an S. And then for the exponent part, you might notice that everything in this row has an exponent of 1 and guess that that would be 4s1. And that's correct. Let's say we were going to go down to this box right here. We were going to identify this electron. The number in front would be 1, 2, 3, 4, 5, 6, 7, because it's in the 7th row. The letter for this whole section seems to be S, so we'd write that. And then our exponent, everything so far in this row has had a 2, which is because it's the second box over, 1, 2, within this section, so 7s2. If we were going to guess about this box right here, you might guess that it was 2, 3, so this one's going to be 4. The letter here seems to be P. And then our exponent in this section seems to be 5. 1, 2, 3, 4, 5. So this would be 4p5. We went down to this box, 2, 3, 4, 5, 6, 7 for its row, P. And this whole section appears to be the exponent of 1. So we can kind of pick and choose now and figure out based on these patterns what those numbers would be to identify some of these electrons. You might notice at this point that there's kind of some chunks on the periodic table that we haven't done anything with. We haven't seen anything in this chunk. There's nothing above it here. And we haven't seen anything with this chunk either. So those would be 2 areas that might be harder to make predictions about, right now at least, just because there's nothing that we've done in that section. So let's go ahead and keep kind of filling in some more here and see. Okay, so after 4s1 would be 4s2. And then after that, we're going to see something a little bit strange. Okay. Your prediction would probably be that this would be 4, but this is actually going to be 3. So there's something a little bit strange that happens when we get to this section with that first number. It's going to drop by 1. So we have 3, and the letter here is also going to change. We're not going to use S, we're not going to use P, we're going to use D this time. And then for our exponent, if you were going to guess our exponent, it's the first box that we've written D in, so you might guess that it would have an exponent of 1, and that's correct. So 3D2, 3D3, and we could continue, and over here we'd still be 3D, and if we wanted to count for the exponent, this is 3, so 4, 5, 6, 7, 8, 9, this would be 10. At this point, if we kind of think about this, we know about the energy level, or the row number, right? That's the 1, 2, 3, and 4, with the one exception of this row doing something weird. And then we've seen S and P show up on here. We just saw D show up on here. So when we think about that, we have one S section that we've seen so far. We have one P section we've seen so far. We have a D section that we've seen so far. So we actually would probably predict that we're going to see F somewhere on here. And if we looked on here and you made a best guess on where F would start, you might guess down here. And that would be correct as well. So this is going to be our F block. Okay. So that's where we would see these. Okay, and when I count across, there's 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Should have counted out loud the first time I counted them. So we see that 14, which goes back to what we saw up here, right? There's a maximum of 14 electrons that can fit into F orbitals total. So we see that. If you look on here, there's this big dark line and then this arrow that goes down, and that's really important. When we see this section, we had 7s2. When we go over here, this is 3, so 4, 5, 6. Remember, something kind of funky is happening here with the row numbers that we're using. This would be D1. And then on the periodic table, the F block, the section down here, really should be cut on the periodic table, and it really belongs right here. These elements, I have my periodic table here. So these elements, lanthanum, element number 57 would be here, and then we would drop down and continue 58 through 71, and then return up here. So the periodic table really should be cut and then spread wider, and then this whole F block should be put up here. But that would make our periodic table really, really wide and unwieldy, and so we show it separately at the bottom. Okay. So for this section, we had S, here we have D, then we're going to have F. The number in front of F is going to be a little bit funky too. We have 7S, we have 6 in front of D, and we're going to have 5 in front of F here. So we'd have 5F1, 5F2, 5F3, all the way across until we got to 5F14. So if I had to make a prediction about what would go here, we're one row farther down, so the number in front would be 6. This is still going to be F, because this whole section is given the letter of F. And then when I count across left to right, this would be F1, so this would be F2. All right, when we look at this, and I'll write this again on page 7 of the notes, but if we look at an example, let's just pick kind of a random box. Let's say that we pick this one, 3S2. This number in front tells us the energy level, which is really which ring in the Bohr model those electrons are going to go into, the one closest to the nucleus, second closest, third closest, fourth closest. The letter is going to tell us the orbital's shape. So when that electron is moving around, is it occupying the shape of an s orbital, which is the sphere? Or is it occupying the shape of the p orbital, which is the figure 8? So it's moving around within that figure 8 region. And then this exponent is going to tell us how many electrons are within those types of orbitals. So in this case, in the s orbital, it's saying we have 2 electrons that are occupying that shape. So number of electrons in this sublevel. Sublevel just means that type of orbital. So in all of the s orbitals, which there's only one at this energy level, there's 2 electrons in it. If we look at this one, 3p6, in all of those p orbitals, there's 3 different shapes. There's 6 electrons total in those p orbitals. Okay. All right, so that's an introduction to what we've seen so far, looking at the energy levels and looking at these different orbital shapes. And we will continue on next time by looking at how we write what are called electron configurations in order to show these electrons.